PM a little bit. This is comments. That was my office. Oh, sorry. Yours on the Microsoft conversion project in Conrad. This is like the project in the driver sheet people Conrad and some people.
Interesting.
Because this is a different location. Yeah, that makes sense.
That's a source of the same to
So we split that element. We're essentially
Are you doing the introduction? Okay, so turn the mic on. You can do it. But then give it to the people you're talking about, what are
but we have
questions.
sounds good.
that's separate by 100.
Very good. So it's the LO. Well, so the LOB is on the residence, like the side being on the code. So the cavity carrier is on the residence. So the cavity, but the side band is what goes into the cavity and at the same frequency as the LO. Yes,
The
exactly.
idea is that feeding the source for this crunch might be challenging. So maybe we try to build the board I over there. Just exciting. And then
The other it's a very nice right is you know exactly where frequency zero should be.
eating just over the it's so maybe you can try the same idea out of there enjoy at the same time
You're in frame starting right about there, so that's perfect. And I can, do some back camera work as well.
Yes,
You have two people on.
All right, good afternoon, and thank you for coming. You passed the test because you found our different group. This is an engineering center. So it's my great pleasure to introduce Sabrina Maniscalco. She's a professor of quantum information computing and logic at the University of Helsinki, and she's an adjunct professor at Aalto University in Finland. She's the vice director of the Finnish Center for Excellence for Quantum Technologies, and she serves on the scientific advisory board of several international institutions, such as the Institute for Quantum Optics and Quantum Information in Aalto, and the Quantum Technology Initiative at CERN. She's the CEO and co-founder of Algorithmic Limited, a startup that focuses on quantum algorithms and software. Sabrina obtained her PhD at the University of Palermo, Italy in 2004. She's held academic research positions around the world in Sofia, Bulgaria, Tehran, South Africa, Turku, Finland, and Edinburgh, UK. She returned to Finland in 2014 to lead the theoretical physics laboratory in Turku, and she moved to the University of Helsinki in November 2020. Sabrina represents Finland's national quantum strategy at the White House in May 2022, and she's a national figure in quantum for Finland. She's coordinated several international and interdisciplinary projects, and she's recognized as one of the leading experts in quantum technologies. Her research is at the intersection of open quantum systems, quantum algorithms, and complex systems. I think we're very lucky that I was able to convince her to join us from Finland. So please join me in welcoming Sabrina.
Thank you very much. It's a pleasure and an honor to be here, and I'm very excited to tell you about some of the research that we are doing in the University of Helsinki. And in particular, this is not related to the company algorithmic, but it's related to my academic career and research and group. And the title may be very technical, maybe for some of you, emergent spatial entanglement in many-body quantum systems. But my goal will be to try to explain in simple terms what it is all about, and especially why this is important for quantum technologies in many fields and for many different, we call them platforms or realizations of quantum computers and simulators. So, but I have to begin by acknowledging the people actually who did the research, and this is the team of the co-authors of the paper of the results that I'm presenting, and in particular Matteo, Via, Elsie, and Boris. Elsie only for part of the work. And here we are in the Swiss Alps, actually, where we were for IBM CUbit hackathon in this case. And I will tell a little bit the story of how is this connected with some of the results that we obtained later on. So I want to begin by emphasizing one of the starting points, which is the fact that initially quantum physics was thought and conceived as a theory that would describe really the realm of the microscopic, so individual atoms, individual components of matter, and as well as quantum of light, of course. But then it was realized over the time that actually the description of systems composing of many atoms of many quantum systems also follow the rules of quantum mechanics, and the border somehow, or the extent to which quantum physics applies, and the transition between the description, the quantum description of our world and the classical one is still very much open and discussed problem, so the transition from quantum to classical. But still, there is a gap somehow in the description of microscopic and macroscopic when it comes to many-body quantum systems. And what I'm going to tell you tries to fill in this gap by identifying ways of describing it which are statistically meaningful and are new. They are borrowed by other disciplines. Now, a little bit of a context, both on the experimental and on the theoretical side. So there have been tremendous progress in the ability of manipulating individual atoms, individual ions, and also not only alone. When I was a PhD student, there were the first experiments, some of them conducted here at NIST, really on single ions manipulation, and at that point, the very first beginning of quantum gates and entanglement between single ions or single atoms started to emerge, and the ability somehow to increase the number of atoms that we were able to entangle and manipulate led to a progress which is now reaching the level in which we are able to coherently address and measure many-body quantum systems. And this is at the basis of quantum technology and at the basis of quantum simulators. And I'm here just pointing out some pictures. I could have taken many others, but it's just an example of the technological advancement that is at the foundation of quantum computing and quantum simulations and of quantum technologies at large. On the other hand, when it comes to numerical approaches, very powerful techniques based on tensor networks have been developed to study numerically, the many-body quantum systems. But I want to tell you something that goes beyond this slide and try to reach a description or a statistical description of many-body quantum systems in ways that are new. And in particular, this experimental advantage, experimental progress led to the availability of a vast amount of data that contain information on the many-body quantum state of the system. If you want to give it more a take that is related to quantum computers, think that the biggest quantum computers existing today is 433 qubit Osprey device by IBM. I'm talking about the circuit-based model. Of course, there are other models of quantum computing, but I'm taking this as an example. In that case, you are able to measure locally the quantum bits, the qubits, okay, all of them. So obviously, this means that you will, in order to characterize the state of the properties of the quantum computer, statistically, you will need to repeat many measurements, and you will have a large amount of data. How do we characterize it? Because these quantum computers are an interesting playground at this point. They are many qubits, they are noisy, they are imperfect, but we are able to apply gates to them and generate some entanglement or generate some properties on demand. So, but how do we characterize their state and their properties? So, in particular, the main question is how do we extract relevant information from systems whose size is increasing continuously in time? What is the framework that we should use? And this is connected with something which is very important, and I'm starting really from the classical side, but I believe it will be very important also on the quantum one, that is the concept of emergence. And I'm not going to give a definition of emergence, but certainly the emergence of collective structures, behavior, and phenomena in systems that are formed of large number of interacting quantum systems has and will play a key role in many fields, be it biology, thermodynamics, chemistry, materials, or gravity. And this is in parallel with what has been happening classically. And in particular, for classical systems, there is a field that is the field of complex network theory that has accompanied the availability of really big data and the need to understand the structures and extract information from this data. And in the framework of complex network theory, really what has been recognized is that a number of diverse systems or data that are related, for example, could be metabolite networks, or could be protein-protein interaction network, but also social networks or technological networks, communication networks. For all of these systems, the complex network theory has provided the theoretical framework to analyze emergent phenomena and also to introduce models that describe their origins. So, and the question is, and this will be the really leitmotif or the main message of my talk, is can we use this toolbox to help us describing and understanding the physics of many-body quantum systems? So this is the framework. This is what I'm attempting to do. And this is motivated again by the progress on the technological side in what we now call quantum technologies. So how about the quantum state? I will introduce a concept that is we call the measurable quantum network representation of many-body quantum states. So what I will present is an example of a many-body quantum model and of a way of describing it using tools of complex network theory. So what is MQNR, measurable quantum network representation? So it is based on something that we have developed called pairwise tomography networks. So in practice, here are the references, and I will tell soon the history actually of these references. But in practice, the idea is the following. Assume you have an n-spin system, but as a matter of fact, you can consider it as an n-body system. So it's quite general, but I will begin by focusing on two-level systems, so qubit of spins. And assume that indicate with rho n the density operator, which describes the state of the n-body system. Now, we all know that the full characterization of this state requires so-called state tomography. This means to have full information of the n-qubit systems. And this is exponentially costly and unrealistic. As n grows to hundreds and thousands, we really are unable to do that. Now, what instead we can do is to look at the reduced density operators. I indicate with rho ij the density operator of a pair, if you want, of spins. And in fact, I will look at all the pairs of spins which are necessary. So this is just obviously not characterizing the full state, but just characterizing the states of each pair of qubits. Okay. Now, so-called pairwise tomography means basically to reconstruct the states of each pair. And this is clearly something which is less costly than the full tomography, but still expensive. Sorry for the typo here. It's still quadratic in n, since you have in the most naive way of doing it, you still have n by n minus 1 by 2 pairs of spins. So it is still costly. Now, what we have been discovering and publishing here, together with a publication by a group of Frank Bilzek and actually this I think is all Google group, Ryan Babush, and so on, is a way of doing pairwise tomography of networks. We specifically focus on networks in a way that is efficient. So in particularly, and I will not describe the details of how we do it, but we discovered how to do it in a way that is that requires only a cost that grows logarithmically. Okay, so it is an exponential improvement. So eventually, what does it mean, and what is the main message here? The main message is that if I have access to measurement of each of the individual quantum systems, I can arrange skillfully the measurements in a way to reconstruct all the pairwise density operator, reduced density operators, in an efficient manner, okay, which scales only logarithmically. And in particular, and now I'm taking a quote by the quantum overlapping tomography paper, they estimated, for example, that if you want to measure every 2-point correlator in a system of, say, 1024 qubit, this would require 4.5 million correlators, and they estimated this is something that is doable in reasonable amount of time if you use this type of methods. Okay, and our method that has been developed slightly after the method of the other two methods, but focuses on the networks, is actually, it has a similar scaling, but a better form factor, and allows to reduce actually the total number of measurements in this specific case by 30% with respect to the other two. Okay. So this is the starting point. I will not describe it in detail. It's just a skillful way of labeling qubits and arranging or grouping measurements, but it allows to collect a large number of information of the many-body quantum systems. And now I will have to tell you how do I use them and what do we do differently with this information. And this is graphically a first subject of what we do. We build graphs, and in particular, there are many ways in which you can build a graph to describe a many-body quantum state. But what we do here is to just identify with the nodes the spins or the atoms or whatever many-body quantum system you have, and with a link that is weighted, a pairwise quantity. It could be concurrency if you want to study entanglement, or it could be purity, discord, classical correlations, any quantity that you can obtain by the two-body operator of the system. Okay, so you do this, and in these graphs that you will see here, you see that the thickness of the line, and very often also the color, is associated to the weight of the link. So these are weighted networks, and this corresponds to the amount of correlation that you have between the two. Now it is clear from these plots that the graph itself contains more information than just the individual pairwise quantity, right? And we will see in which way we can explore this. And also something I will not discuss, but is also very much studied in network theory, is in the framework of so-called multiplexes. A multiplex is really the ensemble, if you want, of all these graphs. And you can study correlations between different layers, and this helps to understand further information. So in this case, you can learn, for example, about the higher order entanglement by looking at plots of this type. But again, I will not go into these details. But another thing you can do is that the different layers in the multiplex can also indicate entanglement, for example, at different times. Then you can study correlation and dynamics in this case. So there's a plethora of ideas that you can implement when you think in terms of complex networks to identify these systems. Now, just a few disclaimers and clarification. These representations, of course, do not give the full information about the many-body states. It's just a collection of reduced density operators, okay? It's 2 qubit in this case, correlators. They don't completely characterize the full n qubit density operator, clearly, but they do tell more than individual pairs. Of course, the correlation between the different layers, I mentioned already before, can give other types of information, like, for example, higher order entanglement. And importantly, this can be generalized to so-called hypergraphs. So if instead of a 2-qubit system, a 2-body system, or the reduced density operator of 2 qubits, I want to consider the 3 qubits problem, so tripartite correlations and tripartite systems. These can be described by hypergraphs, and there is a lot of math and toolbox that describes hypergraphs, so it can be generalized. Now, there have been a number of interesting studies already that use complex network theory in the framework of many-body quantum systems. And I measured here some. For example, this is by Lincoln Carr from Mainz here in Boulder. And here what he did was to use networks of mutual information to quantify the complexity in quantum phase transitions. Again, this is clear applications of the if you want, of the insight that you can get by using this framework in a different context. Then very recently, there has been this paper, this is, I think in December, it was put in the archive by both quantum chemists and quantum information theorists that study quantum correlation in molecules by using networks and networks of discord and classical correlations and so on and so forth. And even in the framework of emergent geometry, and so therefore more quantum gravity frameworks, and networks of mutual information have been used to describe the emergence of space-time. So there are a number of applications, and there's a lot of promising developments and insight that one can gain when using these techniques. Now, again, the first question that comes to mind, or one of the most common questions I've been asked really when I talk about these things is there any connection with tensor networks representation? And of course, there are differences, and I point them out here. So these MQ and R, they make no assumption on the type of states. So they are fully general. You just measure 2-body density operators, and you can then reconstruct the network of any quantity, pairwise quantity you want. They are measurable efficiently. So this is because, as I said, we have developed this way of doing overlapping tomography, and therefore constructing the networks in a not costly way, so log n, as cases log n. And they are generally not giving, however, the full information on the many-body quantum state, but they allow for a more fine-grained description of the correlation flow. And in particular, in a very, very simplistic manner, if I have to plot somehow or identify here, here I have generality or measurability, and here I have amount of information. Tensor networks, they are less general because they impose or they are used for certain classes of states that have certain structural entanglement, but they give more information because they do characterize the free state, while MQLR is more general, but it contains less information on the free state. Of course, the goal here will be to use this framework to understand emergent properties in many models. And now what I will do next is to do so by using a specific example. So I will introduce a model that is very well studied in many-body quantum physics, and I will show you how how a complex network toolbox and techniques are useful in that framework. So that's the next step. And this is the reference of the paper where we describe this, and the model that we will present here is a so-called excess model in a magnetic field. And this is really a model that is one of the most studied models, even has an exact analytical solutions, and it's been used in a million different contexts actually and frameworks. So it is connected to many different applications. And this is how it looks like. This is the Hamiltonian of the model. So I have spin-1/2 systems, and these are the sigma x and sigma y's, of course, are the Pauli operators and the nearest neighbor interaction, and I have a magnetic field. And please notice that J here is multiplying everything. So this model has a quantum phase transition, and it will have that. So it has been rescaled. This is what I mean by this notation. Now, another thing that I will consider is that I will look at open chains, and I will look at systems of finite size. So I want to stay far from the thermodynamic limit, and the reason why I want to do so is that actually, if you are interested in this network analysis, in some sense, gives a meaningful, additional information when you are far from conditions where you have, for example, translational invariance, such that actually everything only depends on distances, right? So instead, if you have finite systems and, for example, clear boundary conditions, and you're far from thermodynamic limits, the effect of the boundary becomes important, and so therefore you don't have. So you need to have more information on all the pairs. That's why the network gives you additional information in this case. But interestingly, this is what very often is the case in standard experimental conditions in many physical contexts. So open chain and finite size is what we will consider. And if you look at this model here, this is a model that in the thermodynamic limit undergoes a first order quantum phase transition from a fully polarized state to a critical phase which exhibits quasi-long range order. And the critical point is V = 1 in this case. So in general, we consider, so the V greater than 1 is the let's say separable state, and then between 0 and 1 we have this phase. I will refer to this reference here, where this model for finite, let's say far from the thermodynamic limit has been studied. This is a model that can be solved analytically, and this is, of course, this will be what I will be using in benchmark. Now, as I said, I mentioned already before, for V greater than 1, you just have this ground state, and the energy of the ground state is minus mv, where V is the magnetic field. But when you are in this region, you have n-level crossing. Again, this is in finite conditions, so before the thermodynamic limit. And in particular, you have certain values of the magnetic field that are given by this expression. And at these values, the system, the ground state really jumps from a subspace to an orthogonal one that is given by this formula. Okay, so you have several transition and several level crossings. And this is the energy of each of these subsectors for the system of the study. And okay, never mind, I will not go into the detail of the math. The most important thing is that you have these different values so these different regions and different values of the magnetic field where you have transition the different laws. And this is precisely what happens, the really discontinuous jump from one symmetric subspace to the orthogonal. No, yes.
You say, are these distinguished, the different ground states are distinguished by different total S Z?
Yes, they are corresponding to the different values of the of K. Yes, it's actually, sorry, let me go back. Yes, so this K number is related to the magnetization, of course, because the total sigma Z is the constant of motion and the proper number. So you have, in this case, there are, so K is an integer which runs between 1 and n and divides the different sectors of the space, yes.
But then in the plane, the spin is ordered. There's a
Yes.
order in the plane, and then you have different projections.
Yeah, exactly. Well, now, what happens is that, again, for this model, I mean, without going into details, you can analytically calculate the concurrence, which describes entanglement, and again, this is the reference, and the concurrence depends on the 2-point correlators of your L and M run across the different spins, and these are the transversal one, while this is the sigma Z. But anyway, it's just to mention that you can calculate this analytically, and using this, we build the networks, okay, which are here. So this is a very first look. I will go over and over different properties of these networks, but this is a very first look of what the pairwise entanglement network look like across the different subsectors of ground state. So these are the different, imagine it as a visual representation of the state, the ground state for different values of BK. And here you are very close, BK equal to 0.99 is very close to the B equal to 1, so it's very close to the phase transition. And you have a fully connected network. And again, it seems rather homogeneous. But then as you move towards the value B equal to 0, you see how really the topology of the network is changing. So really, there are different structures. And I'm mentioning here what the colors are because we will go to this later on. Now, what you see here, the reason why I show here, I don't remember how many spins these are, 20 or 18 maybe, but the reason why I show this example is because this is still at a level in which you can see visually a lot of properties. But of course, clearly you can imagine that when you have large numbers, you don't get visually any information. So you need to have statistical methods to deduct information. Okay, but we will get back to this picture later. Yes.
Can you remind us what these mean? What is the
Okay.
display? No, the pictures that you displayed.
Yes.
What do they represent? What is this pairwise entanglement entropy?
Yes, yes. This just is the concurrence. So it's entanglement that is measured by concurrence. Thanks for asking. I will repeat it. So this is spin number 1. So these are all the spins. The dots, the nodes, are just the spins, and the links is the value of the concurrence between, for example, this spin and this spin, this spin and this spin, this spin and this spin. So it's really the value of the entanglement as measured by concurrence between each of the spins.
Is concurrence just a correlation function? What is concurrence?
Concurrence is a measure of entanglement. This is very much used in quantum information theory. It is defined analytically, really. You can calculate it in this manner, and it is linked. So the analytical formula is linked to the two body correlators. See the transversal one and the ZZ one. So if you look, I mean, you would have, you can also build networks of the two bond correlators if you want. I mean, just that because I'm interested in studying entanglement, in this case I'm looking at concurrence, but you can do it with this.
But they look, all the 2 ones look similar?
They look similar, yes, there are differences, but I mean, it's interesting to look at also at all of them in the multiplex way, things, and also look at if you can get extra information by studying correlations across the different values. But it's a very
But they all simplify as you go to
yes.
larger K.
Yes, I mean, of course, what happens here is that in some cases, concurrence is, goes to zero. I mean, like here. Well, in the sigma x case, I think you have more links, while here you have less, just because just because of separability. I think it will become clearer once I start the analysis. But yes, you can obviously calculate that as well. And I will not talk here about what these colors are, but it will become clearer once I start the whole formalism. So again, here close to the quantum phase transition, and this is you go towards the optimum zero. Now, the question is, these are very much studied model, it's a very well-known model. Can I get new physics, or can I say something new about this model by using this new framework? Because eventually this is what I want to prove. I want to prove that this is useful. I want to prove that there is something more that I can learn if I apply it to this system. And now, in order to proceed further, I have to introduce the measures that are very, very, often used in complex network theory. And in particular, these measures are, I will talk about degree strength. I will not talk much about clustering, but disparities, and then later on about communities, community detection. So let me define these quantities. So basically, I start with the degree, and actually even before defining, I have to mention the fact that I indicate in the following with omega ij the weight of the link. In this case, is the entanglement between I and j as measured by concurrence, but it could be something else. And then in some cases, I will be interested only in the topology, which means not in the weight, but just in the presence or absence of a link. Okay, this is generally what we identify the structure in terms of topology. And in this case, I use Aij, which is just a beta function. So this means entangled versus separable. Okay, it's a 0 or 1 type of information. Okay. Now, degree and strength account respectively as the degree accounts really for the total number of connections in the node. So it's the number of links, so the degree of the red dot is 3 in this case, is the number of links which arrives to the node. And the strength takes into account of the weight. So it's the total weight of the node. So it is the sum of these numbers which corresponds to the strength of each one. And disparity instead quantifies the heterogeneity of the distribution of the weights of the connections to the node. And it's defined in this manner, okay? Mathematically, it's defined in this way, where S is the strength and omega ij's are the weight of the links, so it's the amount of pairs content. Okay? And this is really a measure of how heterogeneous is the distribution of weights in the network. But it's a local measurement, okay? So it's how heterogeneous is the distribution of weights around a given node. So they are all local quantities, they measure local. Now, for example, for disparity, if all the connections have equal weight, then like in this case, then the value of the disparity is just equal to 1 over the degree of the network. While on the opposite, if one connection dominates, the disparity is 1. So think when I look at the disparity, if disparity is 1, that is the maximum level, it means that I have a situation in which, like here, one connection, this connection dominates with respect to this other one. So when I have, disparity is unequal in it. It shows that there is something unbalanced in the links. Okay? Now, let's have a look first at the disparity and how the disparity goes for the model I described before in terms of across the nodes. Now I have 180 spins. These numbers is the number of spins. So I have 180 spins, and what I'm changing here with the colors is the magnetic field. Okay, so I'm going from 1. Remember, 1 is close to the phase transition. So it was this network that was fully connected. And 0 is so where I just have pairwise correlations. And what I see is the disparity shows a very different behavior, and in particular, close to the phase transition. Again, I remind you, it is in this way. It is characterized by a very uniform. It's characterized by a very uniform distribution which looks as if everything is homogeneous, right? If you look at it, you would say, yeah, it seems very homogeneous. The disparity, the local disparity, it's minor, seems to be very, very small. Okay, just because everything is fully connected. So each node is approximately having very similar links to whatever it has around. However, if you look at the strength, so if you now take into consideration how the weights are distributed, look, this is the curve for the specific value. This is what you have to look at. And the strengths are actually very heterogeneously distributed. So this means if you look here in the bulk, and what is known as the bulk, the weights are much higher than in the boundary. Okay, so this is something that you extract from the strength, not from the disparity. And so and somehow it tells that it's very non-trivial the way in which the entanglement is distributed for this specific type of chain. So in particularly, why it seems homogeneous from this plot, it seems actually that there is more symmetries here. And in fact, they are heterogeneously distributing across the systems, but the weights are allocated in a way that all the relevant, relative fluctuations at local level are equal. So if I look locally, if I look here, okay, and if I look here, the fluctuations are really all equal. And in order to test this hypothesis, you can look at this at the distribution of strengths rescaled by the mean value. And if you plot this, you will see that for all the different pairs, all the curves collapse. And what this means basically is that there is a very high level of non-trivial symmetry in the ground state, very close to the phase transition. And this is just, so until now, there is no new physics, but there is a new way of looking by means of these tools at the properties of pairwise entanglement very close to phase transition. And now in the next case, in the next part, I will go to new physics for MMR, and I will talk about the entanglement topological instabilities. And in this case, I switch to the unweighted network. So I will describe how certain instabilities are present in these systems in the case of entanglement. And now I remember before I looked at strength, so at the weighted links, and now I'm looking at the unweighted links. So just the presence or absence of a link, meaning separability versus entanglement. So I look at the unweighted network, and this is what we discovered. So what I'm plotting is the average degree of the nodes, okay? And in this case, I'm plotting it across the relevant values of the magnetic field between 0 and 1. Again, 1 is the phase transition point and 0. Now, the average degree per node behaves in the following way. So here I'm increasing the magnetic field, and I'm increasing it towards the establishment of quasi-long range order. And what happens is that the average degree exhibits jumps, the average degree per node. And jumps only characterizing, so, from 2 to 4 to 6. So only even values seems to be established. And this is the different curves are for different values of 50 to 100. You see clear transition points for the magnetic field in which I go from, what does it mean, degree 2? So degree 2 means that the nodes, so means that each node has 2 connections. Okay. Degree 4 means that each node has 4 links, so 4 connections. 6 and 8 and so on. So as you go towards this quasi-long range order in the entanglement, you see that the type of links jump from 2 to 4 to 6 to 8. So you have a 2 body, 4 body, 6 body, and 8 body. Why do I talk about that? And this is a topological features really of the system. Okay, why instabilities? In order to understand this, we have to look at the fluctuations of this fragment. So, and here I'm showing the fluctuations in the degree. So this is the average value of the degree, and this I'm showing the fluctuation of the degree as a function of K over N. Again, it's the same thing. So as I go move the magnetic field value, and what I see here is that at this, so these dashed lines are precisely this. The value at which I have the jump from 2-body to 4-body correlations. And at these jumps, I have fluctuations which remain finite also as I go towards the thermodynamic limit. So this means that actually these jumps are accompanied by fluctuations. And this is what we call instabilities. Okay. And you see that these points remain again as I increase the value. So the graph, this means that the graph is not degree regular at the transition point, and this is not so even in the thermodynamic. And this is something which is, in some sense, can only be discovered through this analysis. And this is something which characterizes and for which we are, in some sense, establishing, an intermediate analysis which goes beyond thermodynamics. So it is a gradual movement towards the behavior of finite systems and towards instabilities which describe the onset of longer range order, and in particular the onset of entanglement that involves not 2-body but 4-body, 6 bodies, and so on and so forth until you obtain them. And then the second, actually the third point that I want to discuss here is another phenomenon which is now more mesoscopic. So, and everything I described here is somehow local because I described the degree of the nodes. Okay, so this means properties of the pairs of atoms in a way. But now I want to go beyond and describe more mesoscopic processes. And this is what I will do here, and this is related to the title of my talk, that is emergent entanglement and spatial structures. And we are looking now at more mesoscopic systems. Now, I'm using a method which is extremely well known in complex network theory to detect communities. So, what are communities? Communities are parts of the network that are characterized by a larger number of connections, for example, to describe in a very simple terms. Okay? So networks are not regular, especially real networks. They present certain community structures, and they are identified by the presence of an increased number of connections in certain regions, and they have to, and in order to, they're called communities, but in order to discover them, you have to use methods or algorithms that are developed, appropriately, so to extract these mesoscopic structures. And one of them is this LPA semi-synchronous community detection algorithms. There are books only on community detections. I will not go into details. And we use this one because it was open source available, and we modified it for weighted networks. So we are looking for these mesoscopic structures now. So for regions in the network where we observe a higher density of connections over links. And an important thing to mention is that this type of algorithms, they do not know anything about the underlying graph. They don't know about the position of the atoms. If this is a chain, and I would number the atoms as 1, 2, 3, 4, 5, depending on their positions in the chain. This type of metadata are not included in these algorithms. For the algorithms, the nodes are all the same. Okay? So they just give them a bunch of nodes and links, and the algorithms extracts communities from them. And now we are looking at these community detection methods, and we run them for the data that we have for these graphs. And I'm showing here 2 curves. The first one is for the weighted, and the second one is for the unweighted networks. But I look at the weighted ones. And as you can see here, NC is the number of communities, and K over N again is the magnetic field, once again, but I'm going now from 0 to 0.5 because the other one will be similar. And what you see here is that there's a perfect correlation between the radius of the magnetic field, in particular the value of K, and the number of communities. It's just a line. And this is interesting because this is precisely what you have seen here in this plot with the colors. So K is this quantum number ranging from 1 to 10 in this case. And as you see, for K equal to 1, very close to the phase transition, there's the algorithm detects only one community. And in fact, each spin is entangled with all the others here. This network is fully connected. For K equal to 2, the algorithm detects two communities. And in fact, you have two regions of entanglement in terms of pairwise connectivity. 3, 4, 5, and so on and so forth. And in fact, as I said, there is a one-to-one correspondence between the number of community and the number K. It is a relevant quantum number describes the total magnetization. So in a way, the algorithms allows to extract region of entanglement which are located in space, really, because this is really the space of the chain, without having any a priori information about the positioning of the field. And this is quite interesting because, as I said already many times, this K is the quantum number that is associated to the total magnetization of the field. So it is related to a global symmetry of the property of the system, a global property of the system. And it is emergent from an analysis that is absolutely agnostic about any of the specific physical locations of the space. And in particular, you can see also, you can analyze the average size of the community and the average size of the community of N over K. And it's it was interesting for us to discover that in a completely different fields of physics, many years ago, in this paper, the same model was studied. Yes, the same model was studied. And it was discovered that if you look at the XX model, you can describe it as well in terms of a so-called dual basis, defining this way. Now, this dual basis creates a topological excitation, they call it kink, when acting on the fully polarized state. And it's interesting because they describe the different ground states across the different sectors in terms of the behavior of kink, anti-kink pairs. And in particular, a single spin flip, which is the action of this operator on the fully polarized state, create a kink anti-kink pair. And the state with K spin flips is a combination of kink anti-kink pairs. And if you look at it, really, the way in which they look at it in here is in terms of very close to the phase transition. They describe this state as a sea of condensed kink anti-kink pairs. And as B decreases, they say, again, I'm really using their words, what happens is that you have an increasing number of kinks of decreasing size. And look how visually, how tempting it is visually to associate this with the community structures in the entanglement networks that are detected by the algorithm. So we conjecture that the emergent entanglement structure that we observe in this spin chain precisely reflect the structure of kink anti-kink pairs in the dual representation. That is a very mathematical description of the system applied to a very different field, but still that can visually relate very much to the network framework that we described. So I'm close to the conclusion. I will give a summary here. the main points of my talk are that MQNR are an efficient, measurable representation of the state of a many-body quantum system. And this is done in terms of networks of pairwise quantities. So what is appealing here is that on the one hand, you have a difficulty in analyzing the state of many-body quantum systems as the number of the quantum system increases, and this difficulty, I mean, is mitigated by the fact that perhaps you can measure nowadays two-body or three-body reduced density operators, and the question is, what can I say with this partial information? And on the other hand, you have this opportunity of using this plethora of tools that have been discovered in complex network theory and successfully analyzed for, you know, in completely different scenarios, really, to study the brain, to study communication systems, to study the internet and so on. And the question is, I mean, how much insight can we gain in the physics of many-body quantum system if we start using these tools that are so advanced? I find it very fascinating. And this representation is, you know, as I said before, particularly useful whenever you really have, you know, still many qubit systems, but you have open boundary conditions, you don't have translational invariance, where the properties of the correlations do not depend only on the distance, because otherwise, obviously, you don't need to have the full network. And then we demonstrate the power of this representation by showing we take a model that has been extremely, you know, well studied, and we say something new. We say that there exist spatial structures in the entanglement that were previously undetected. We did specifically three things that the paper has results with the emergent entanglement community structures. We also studied introduced the presence of topological instabilities that are accompanying the onset of the quasi-long-range order in this spin chain. And this is another result that I didn't discuss, but if we discovered self-similarity in the bulk of the pairwise entanglement. But this is a result I have time to describe here. But it's again something that is brought from the analysis of the network theory. So take-home message. I really think that they are very promising tools that need to be used more and more as we embark in this challenge of understanding the properties of quantum simulators and many-body quantum systems that we can control. Per se, I also believe that, as it is the case for classical physics, to describe complex quantum systems, this provide a very interesting framework to describe emergence, and also to provide this sort of mesoscopic analysis that comes from the underlying microscopic constituents, but it also gives something more. It is something which it is not deducible only from the microscopic local interactions. But allows to describe this more mesoscopic, like the community. Future direction, we want to apply this to the case of molecules. I mentioned one of the papers, and indeed two of the authors of that paper are working this time in my startups. And it's interesting to apply this to emergent geometry from entanglement in quantum many-body systems. This is something that one of my PhD students is doing, more related to the quantum gravity applications. And very interestingly, they can be very, very useful to benchmark quantum computers and quantum simulators. This is everything I wanted to say, and thank you very much for your attention.
Thank you for the fascinating talk. I have a question about the topological instability that you showed. Maybe it's even maybe useful to show the slides. Yeah.
Oh no, maybe I should just go.
The extras.
No, an extra.
Yes, this one.
Yes.
So I just wondered what happened if you instead use the strengths here instead of the theory. Like the average number of the strengths and the average fluctuation of the strengths, then does it ever give a like continuous like
So if I use that.
strengths instead of the
Yeah.
So I just wondered why the
Yes.
degree is a good, you know.
Yes. Of course, but if you look at the strength, you don't see the instabilities themselves, because the instability they come from. So actually, you don't see these jumps because the jumps they actually, you know, I think you have it here. This is the gain they are doing. So, but it gives an indication. So this is for the community detection, but you see here the weighted would correspond to the strength, right? The weighted is not sensitive to these transitions here. These transitions here are now related to the community, and you see the transition appear for the unweighted, that is the topological instability. Now these lines here, these values of the magnetic field are precisely the same values of the instabilities. Okay, so they are these ones. So the reason why I jumped to the community detection is that also the community detection reveals precisely these transition points, but in the strengths you don't see that. You see the curve is just a line. So you see it only in the topology, but not in the strength. So it's continuous.
Thank you for the talk. So in the introduction, you said something about the benefit of the theory for quantum applications, quantum technologies. Can you comment about that? Because I think you didn't say anything about it.
Yes, of course. It's true. I did and I did not, because if you look at this, wow, because if you look at this as a 2 points. Imagine that this is a quantum simulator of a spin chain model. Then, of course, this is allowed to say something about the physics of the exerts model on a quantum computer that would be a quantum simulator. But if you think in terms of different applications, like for example for chemistry and molecules, what you can do, you can study, and what is the topic of this paper here, which perhaps I even, I will show it to you because I think I have it open in the PDF. Let me just, I want to go, oh, is it possible to, for some reason, is it possible? Yes, now it worked. And there is, okay, I think it's, yeah. Do you see the screen? Yes, you see this. Okay. Let me, maybe I would like to remove this.
Yeah, I got it.
So I will not go in the details of what this is, but this is the application to the description of molecules. So if you want, one of the main use cases or maybe potential future applications of quantum computers as quantum simulators are for the description of, for example, ground state or excited state of molecules. So in this case, you have generally what you do is Fermi to CUbit mappings, and then you encode the state of what would be close to the ground state or a certain state of the molecule into the quantum computers, and then you can use, for example, variational approaches to move towards the real ground state of a given molecules. However, what is still a big question mark is, what is the resource there? So, I mean, why is the ground state of a quantum computer, of a molecule, of a given molecule, difficult to simulate classically? Is it because there is, in the ground state, there is maybe in stretch configuration, actually, at the fermionic level, there is entanglement that is reflected then in the CUbit structure, I mean, or not. These are open questions, okay? So what here they did was to visualize in terms of networks which are much smaller. Correlations, classical correlation, quantum correlation, and entanglement in particular, for certain molecules in the ground state, using certain, I will not have time to discuss the specific quantum chemistry methods. And the goal was really to understand if this is the case, and which is actually the resource here. Okay, so is it entanglement or is it quantum discord, for example? And this is important because many things are, the presence of entanglement in the molecular ground state and the amount to which and the location of this entanglement as a consequence reflect in the simplicity, if you want, in the circuit depth. If you want to use gates to initialize the quantum computer in a state that has a certain amount of entanglement, a certain structure entanglement, in CUbit space, you need to know beforehand what this type of correlations are, what this type of, and how they are distributed across the CUbit, across the network. So this is an example of an application where, and of course, in this case, I don't know how many spin orbitals they used, but this is an example in which they use networks. They are visualized in a little bit different manner, but they use networks of different types of correlation, visual information, classical, discord, and entanglement, to understand what could be potentially the resource and why quantum computers would be useful, when they are useful, and how complex it is actually the implementation of the circuit that would initialize the computer.
Thanks for the really interesting talk. I'm just trying to build some intuition about what structure of different physical problems might make this an interesting tool, or something where you might expect particularly interesting physical results. So this XX model that you've shown has like local pairwise interactions. Do you expect, and you were saying it's interesting when you have these like open boundary conditions, for example, do you expect that these systems based off of these like pairwise metrics will give interesting insights if you have like three-body or non-local interactions throughout your spin chains?
Yes.
Or all-to-all?
Yes, it's a very good question. Yes, of course, so first of all, one need to distinguish between the physical really interaction at the level of the Hamiltonian and the network links, because the network links in this case are links of any pairwise correlation. But of course, in a way, the correlations are, they can be reflected if I'm looking at ground state from the presence of from the structure of the Hamiltonian. But you can also think in terms of dynamics, where you could imagine to have a quench, for example, in the system, and then dynamics and correlations evolved, and therefore correlations that maybe did not exist between pairs of spins. They are induced by the dynamics itself, for example, after a quench. So in general, I would say that clearly in molecules is obvious, or in anything which does not have a strong translational invariance is obvious, because clearly we always need more than just a number which is the distance between the correlation. Let's say that the correlation function will not depend only on distance for all of the pairs. This is what you, because then you don't need it's let's say the network is it is redundant, exactly. So you would need to, you think in terms of whether cases in which the either finite size or it can be not regular structures on lack of symmetries or all the conditions that very often are also very realistic in terms of physical examples. So because if I have, I don't know, crystal of ions, maybe they have obviously binary conditions that are very physical and very real. They have finite size and so on. That's a good point. But in dynamics, also friends can live with correlations.
So thank you all so much for coming. Is there additional questions you can ask? Let's thank her for coming.